Welcome to 53B. Now, I'm calling it 53B because it's an extension of lesson 53 in the book. But I do mean extension. It goes beyond what's in the book, actually. But I think it'll help set us up a little better for the second half of 54. And besides, this is like some of the funnest graphing you'll ever do in your life. So let's enjoy it. Okay, so polynomial functions, right? So what's a polynomial? That's where you've got some kind of a number. This can be any real number, really, as a coefficient to x. And then this has to be a whole number, 0, 1, 2, 3, and so on. This can be any real number. And you have a whole bunch of terms like that. So you might have, plus others, other similar terms. So you might have like 5x squared plus 3x plus 2, or, whatever. Those are polynomial functions. So in order to get at the general polynomial functions, what we're going to do first is look at some very simple ones, some monomial functions, which means it's only one term to it. And let's look first at the ones that have even powers. And we'll just have coefficients of 1 just to keep it even easier. So we've got this x squared, x to the 4th, x to the 6th. I want to graph all three of those. So I'm going to make a single xy table. So x, and then we'll have y equals x squared, y equals x to the 4th, y equals x to the 6th. Let's just kind of make a triple xy table. I want to plug in a nice little spread here, -2, -1, -½ 0, 1/2, 1, and 2. Okay, for my x values. So if y is x squared, -2 squared is 4. -1 squared is 1. -½ squared is a 4th. That's a 0, and then you get the same numbers over here, right? 1/4, 1, and 4. If you take a -2 and you raise it to the 4th power, you're going to get a 16. A -1 to the 4th is a 1. This will be a 1/16, 0. And then these will be the same on the other side, right? 1/16, 1, and 16. If you take a -2 and you raise it to the 6th power, you're going to get a 64. But if you raise a -1 to the 6th power, you get a 1. And then this will be a 1/64. Isn't the pattern in this table kind of cool? I like the pattern in this table. It's cool, man. It's cool. So I'm going to start graphing this one first. So when x is -2, we got 4. So that's about here. When x is -1, we're at 1. When x is -½ we're at about a 4th, somewhere about there. 0, 0. When x is +½ we get a 4th. When x is +1, we get 1. When x is +2, we get 4. And of course you recognize a really nice parabola. A parabola. So this is x squared right there. Okay, cool. Now let's graph this one. So when x is -2, we're at 16. We're off the charts. We are off the charts. But notice when x is -1, I get 1 again. Now when x is -½ I get way down at the 16th, way just hugging the axis. Then I go through 0 again, then I hug the axis again, then I'm here again, and then so it's like, notice that if you're close to the origin, you're underneath the old parabola. But once you get past x equals 1, you're climbing much faster. Or if you get past -1 going the other way, you climb much faster. So this is what x to the 4th looks like. Notice I'm not going to do x to the 6th. It'll get too busy. But you can see that we're basically heading towards, as we keep increasing the exponent, 2, 4, 6, 8, 10, 12, and so on, we're sort of heading towards, well, it's going to be really flat there, and it's going to be really vertical there. It almost looks like a U-nail or something. We're heading towards this as n becomes humongous, like towards infinity. So they're all kind of parabolas. They all kind of open up. I think of them more as like a field goal, goal post for a field goal or something like that. But notice, this is kind of interesting. All of them are going through the point -1, 1. All of them are going through the point 0, 0. All of them are going through the point 1, 1. And it's what happens in between that's different. So again, in here, the higher the power, the lower you are. But out here and out here, the higher the power, the faster you climb. And that's your basic behavior. So I'm just going to say 3 points in common. Just kind of point that out. 3 points common to all. Exclamation point. Cool. Now let's look at odd powers. So I'm going to do another one of these multi-purpose XY tables. So we're going to look at x cubed, x to the 5th, x to the 7th. What are we getting here? Well, I'll kind of make different columns for x cubed, x to the 5th, x to the 7th. Something tells me we're going to need a longer table than that. But I'm going to plug in the same kind of numbers, -2, -1, -half, 0, 1/2, 1, and 2. So starting with this column, if you plug in a -2 and you cube it, you're going to get a -8. A -1 cubed is a -1. A -half cubed is a -1/8. 0 cubed is 0. Half cubed is an 1/8. 1 cubed is a 1. 2 cubed is an 8. Cool. So if you kind of notice, you know, we kind of have this same pattern here and here, and we kind of have this same pattern here and here. The main difference being that it's possible to get negative y values. But other than that, it's kind of a similar deal. -2 to the 5th power is huge, -32. But -1 to the 5th power is -1. Yay! This will be a -1 over 32, and I'll bet you can guess what happens next. Over here, a -2 to the 7th power is even huger. It's a -128, my goodness, but that's a -1. And I'm pretty sure you don't actually have to plug these in. You can kind of tell what the pattern is here, right? And this is a 128. So I'm going to graph x cubed first. What does this thing look like? Well, when you plug in -2, you're already off the chart at -8. When you plug in -1, you're at -1. That's nice. -half, I'm at -8. 0, 0. 1/2, I'm at an 1/8. So I'm trying to draw an 1/8. When I'm at 1, I'm at 1. And when I'm at 2, I'm at 8. So it's kind of going something like this. Notice it's momentarily horizontal. When you get to the origin, it's actually just for a moment, it's kind of horizontal. So that's my x cubed. Make sure I put my arrows on there. Now let's do x to the 5th. -2, -32. That's way down. But notice it's going through this point again. And we get that same behavior. Now I'm at -132, so that's like even further. So when you're in here, when you're in between -1 and +1, it's kind of hugging the x-axis more, like this. But then when you're out past -1 this way, or you're out past +1 this way, it climbs faster. So that's kind of similar behavior. So this is heading towards sort of like a, not a field goal necessarily, but a sort of a field goal that kind of got bent or something. Something like this, with arrows like this, as n approaches infinity and is an odd number. So again, the higher the exponent, out here, if you have a higher exponent, you're climbing faster and faster. But in here, if you have a higher exponent, you're hugging the x-axis tighter and tighter. So it's kind of interesting how that works. And then notice again, we got 3 points common to all. -1, -1 is a point on all of them. 0, 0 is a point on all of them. 1, 1 is a point on all of them. They all go through those 3 points. So I'll point this out again. 3 common points. And by the way, none of these are a straight, well, I guess you would have a straight line if you were plotting x to the 1. But other than that, they're not straight lines. They're like, it's like a crooked propeller or something like that. Okay, so cool. So now we've got a look at how these very basic polynomials, the ones that have only one term, monomials, what they look like. It depends whether your exponent's even or odd. All of your even exponents, they're going to look sort of like field goals, or up, they're going to open up almost like parabolas. And then all of the odd ones, come on you, all of the odd powers, they're going to look almost like somebody took the left branch and kind of bent it down like this. Okay, now that actually even though we're going to be playing with much more complicated polynomials, knowing this much is actually huge, because it turns out knowing how these things behave, x to the even, x to the odd, knowing how those things behave tells us something about every single polynomial function you will ever want to graph ever. And that something that it tells you is called end behavior. The end behavior, which means what's happening way out. By end, we mean over on this end, over on this end, like way, and I'm talking way, way out towards infinity, towards negative infinity, okay? So end behavior means what's it doing way out there? What's it doing way out on the wings? And it turns out that you know what it's doing way out on the wings just by looking at your lead term. Now I'm assuming it's in standard form. You put the high exponent first. That's properly called the lead term. But this polynomial is going to behave like x cubed, and we now know what x cubed behaves like. X cubed behaves like this. This polynomial, even though it's got some funky stuff added, is going to behave like x cubed, but not in the middle, just on the ends. So out here and out here, this is how it's going to behave. Let me try to clean this up a little bit. Let me repeat and clean it up. Okay. End behavior for this function will be y equals x cubed. And remembering from over here what y equals x cubed looks like, you say that means it's going to way out on the right, it's going to be up here rising fast, and way out on the left, it's going to be down here sinking fast. This is called your end behavior. Notice I didn't say anything about what's happening in the middle. All of these funky terms, in fact, are going to change what happens in the middle. This is not going to be a graph that looks exactly like x cubed, but it will when you're way out to the left or when you're way out to the right. That's called end behavior. And by the way, why does that happen? Well, we've kind of seen this idea in a different context. Let me, come on, that's not what I want to be doing. Okay, I want to redo. Come back, come on. Redo 14 times, 14 times, 14 times, 14 times, 14 times, 14 times. Okay, that's good. I wanted my end behavior back, man. This is my end behavior. I wanted that back. Okay, so I got it back. Good. So anyway, the question was, why, how can I say that? How can I be saying that when I'm way out at x towards positive infinity or negative infinity, that it's going to look just like the graph of y equals x cubed? How can I say that? I can say that because, correction, we haven't seen this before, but we're going to see it again coming soon. Okay, so anyway, it happens because, think of this as, instead of plugging in infinity, plug in something like really big, like 1,000. Just plug in 1,000. It's not infinite, but it's big. This is 1,000 cubed. And 1,000 cubed is 1,000 times 1,000 times 1,000. This is only 1,000 squared, which is only 1,000 times 1,000. And then, yeah, you multiply it by 3, but la-di-da, right? If you compare this number here, which is 3 million, to this number here, which is, what is that, 1 billion? You can tell that this term's going to be more important. It's going to be a bigger number. It's going to be more important. You're going to be having, when you plug in x equals 1,000, you're going to have basically the billion coming from the x cubed term there. And then you're going to add a little bit, subtract a little bit, and then subtracting 12 from 1 billion is not going to mean a thing, is it? No, it's not. And then consider if you plugged in not 1,000, but you plugged in 1 million. Well, this is 1 million cubed. That's 1 million. Okay, cube it means add 6 more zeros, and then add 6 more zeros again. That's big. I don't even know what that number is. Let's see. That's millions, billions, trillions, quadrillions, penta-wow-wows. That's what that is. That's penta-wow-wows. That's humongous. Whereas if you only squared it, then you'd have 1 million, which is big, but then you'd add to square it, you'd add 6 more zeros again. Now, if you compare this number to this number, you can tell that this is starting to dominate. This is starting to take over. Take the national debt and subtract $3. Did you really change the national debt? No, you didn't. That's kind of what's going on here. The lead term is the national debt. And then this is me and you trying to pay it down. Good luck. So this is what I mean when I say that the lead term is going to dominate. As you get out on the wings, as you get way out towards positive infinity or negative infinity, the lead term is going to define what your graph looks like. When x is very, very huge, you only have to look at that first term and say, well, what does y equals x cubed look like when x is huge? Well, it'll be out here, it'll be out here. It'll be rising on the right, it'll be sinking on the left. I know that from this, right? It'll be rising on the right, it'll be sinking on the left. I know this. So that means I know the same thing about this function. More examples. Here's one. So again, when x is really, really big, talking huge, talking mega huge, talking approaching infinite, then infinite to the fourth power is a whole lot bigger than a mere infinite squared. I mean, you take or maybe I shouldn't use the word infinite. I should use the word billion. If you take a billion and square it, this is a billion, and then you raise it to the fourth power. It's a billion times bigger. That's huge. So these terms just pale in significance. They don't matter anymore when you're way out on the ends. And so the end behavior is you just look at the first term, x to the fourth. Then you ask yourself, what does x to the fourth look like anyway? And you come back up to here and you think, oh yeah, I remember what x to the fourth looks like. It's basically one of those field goals. It's like a parabola-ish thing, a very U-shaped parabola. But it's going to have end behavior it rises over there and it rises over there. That's my end behavior. So whatever this function looks like, and it could do lots of different things in between, it's going to look like that on the left end, that on the right end. Here's a cool one. The end behavior here would be y equals, again, it's in standard form. The highest exponent comes first. That is important because, my argument only works if you're talking about looking at the highest exponent, right? The highest exponent's going to dominate. So the highest exponent is the x cubed. That term is going to dominate. You have to think of the whole negative 2x cubed. That's what this is going to approach when you're way out on the wings. Now, what does that look like? Well, x cubed, remember, does this. And then what's this going to do? That's going to be a reflection across the x-axis. In other words, that's a reflection up and down. So what this thing is going to look like is this. Except again, it's not going to look like that everywhere. It's only going to look like that when you're far to the left and far to the right. Again, hence the name end behavior. How does it behave on the ends? And one more. Here's a funky one. Wow. Okay, so we got to figure out what the lead term would be. Now, I suppose you could say, yeah, let's FOIL it all out. Yay! But you don't have to FOIL it out because all we care about is what's the first term going to be. And the first term is going to be, well, it's going to be, you're going to have to multiply the negative x times this x. And then it's also going to be multiplying, notice this is an x being squared because this would get FOILed out and you'd have an x squared. And then this one is also an x squared. Okay, so the end behavior, this is going to look a lot like a negative x to the 1, 2, 3, 4, 5, 6. It's going to look like a negative x to the 6th. So this is x to the 6th. Remember, this is one of our even functions. It's going to look something like that, but then reflected, which means it's actually going to look like this. And so our end behavior is way out on the left. We're down here in the third quadrant, and way out on the right, we're down here in the fourth quadrant. So here's our answers. So this polynomial has this kind of end behavior. This kind of polynomial has to have this kind of end behavior. This polynomial must have this kind of end behavior. This polynomial must have this kind of end behavior. And knowing how it behaves on the ends, then you can get started graphing things in the middle. Okay, so we will be using this later. So one more key concept here, and we'll be ready to rock and roll making some groovy graphs. And this concept is called multiplicity, and it has to do with how does a graph behave at an intercept. Behavior at an x-intercept goes according to this. So we'll illustrate this in a minute. But if you have an even multiplicity, it's going to bounce off the x-axis. Maybe do this, maybe do this. If you have an odd multiplicity, it's going to cross the x-axis. Maybe this way, maybe this way. Okay, so that's the basic idea. Where do you get the multiplicity from? It's basically the exponent. So to illustrate this, first of all, I started with just x squared because we know what it is. I like to start with something that we know what it is. We know what that looks like. It looks like that. Now the lingo that I'm trying to introduce here is we would say that we have an x-intercept at 0, and it has a multiplicity. I don't know where they came up with this word, but multiplicity of 2, because that's what the exponent is. Now because that's an even exponent, that's what this says, you know that it must bounce off the x-axis. And of course it does. We do that. Now look at this one over here. Where's the x-intercept for this thing? Well, you would set the function equal to 0, right? So if you set the function equal to 0, you very quickly figure out, oh, the x-intercept's at 2. So the x-intercept is at 2. Come on, you. Let's draw an x-intercept. Okay, so the x-intercept's over here at 2. And by the way, this is going to be basically at heart. This is an x to the 4th. In fact, that would be the end behavior, right? Because if you foiled this thing out like crazy, your first term is going to be an x to the 4th. And so you can get your end behavior from x to the 4th. And remember what x to the 4th looks like. It looks kind of like one of those, not a parabola, but sort of a parabola. X to the 4ths do that kind of stuff. So we know it's going to be going up, basically. So the x-intercept is 2. And we have multiplicity of 4. And that's okay, because it's even. And even means it'll bounce. So I'm expecting something like this. It'll be sort of like an x to the 4th looking function, except kind of shifted to the right by 2. That's what I'm expecting for my graph. Okay, but the point I want you to focus on is simply that this x-intercept has an even multiplicity, so what we really know is that it bounces off the axis. Okay, cool. X cubed, we remember what that one looks like. It looks something like this. Notice the x-intercept is at 0 with multiplicity of 3, because you're looking at the exponent, so I probably should have pointed this out explicitly. This has a 4 for an exponent. You've got the x-intercept is at 2. The x-intercept is at 2 with an associated exponent of 4. Here the x-intercept is at 0 with an associated exponent of 3. That's a multiplicity of 3. And since 3 is an odd number, guess what? It says it right up here. Odd multiplicity means you cross. So it has to cross. And of course we knew it did. I mean, that's crossing. That's crossing the x-axis. This one. Well, we know something already. We know that it has an x-intercept at -4 with a multiplicity of 5, which is odd, and so it'll cross. So I don't know what the rest of this thing looks like because it's got this -2 that's kind of bothering me. But I know that when you're at -4, back here someplace, it's going to cross the axis, which I'll usually put like a little C there to tell me it crosses the axis. Actually, we can figure out the end behavior right now, right? So the end behavior, that's a B. The end behavior would be, well, you'd have the -2 multiplying the x to the 5th, because if you foiled this all out, the first term would be an x to the 5 multiplied by a -2. So it's going to be a -2 x to the 5th is your end behavior. And what does that look like? Well, remember, x to the 5th is one of these, but when you put the negative on, it reflects it. So it's not going to be one of those. It's going to be kind of like this instead. So this is going to be doing something like, I don't know, something like this. We'll come back to this example later, but the point I wanted to make here with the multiplicity, I know that I'm crossing at the x-intercept of -4. This is something I'd like to come back to in a little bit. We've got enough information now. We should start banging out some graphs. Now I've got this, 3-4 step plan here for how to bang out a graph of something like this. Nice polynomial function. Factor first, okay. The reason you're doing that is because it makes it a lot easier to find the intercepts, which are key information. Then, thinking about both end behavior and multiplicities, hang a nice wet spaghetti graph on your intercepts. All of these polynomial functions, they all have graphs that are just wet spaghetti. Well, they don't turn. This fails the vertical line test, so that was a mistake. But they don't have sharp corners. They don't have gaps in them. Nothing like that. They're just all nice wet noodle graphs. So, what does the degree rule have to say? I'm going to worry about that in example 4. We're not going to worry about that right now. So, here we have a nice polynomial function. Let's graph this thing. So, step 1, I want to factor. So I see 4 terms. I'm going to try that grouping thing. So looking at the first 2 terms, I could pull an x squared out of the first 2 terms. Okay. Looking at the last 2 terms, I could pull a -4 out of the last 2 terms. Remember that has to be a positive 3 because -4 times 3 would give you the -12. Continuing, I have a common factor. So I'm going to ignore it for a moment. And then I'm going to put it back. This has the same effect of, notice that this is like I distributed x squared times x plus 3, and then a -4 times x plus 3, right? It gives me the same thing. And then our finished factored form is to do this difference of squares thing. So I've got an x minus 2 and x plus 2, and then I've got that other x plus 3. And here is my fully factored form. Now this is beautiful to work with. I want to find intercepts now. My y-intercept, actually that's a good way to find the y-intercept. Remember, you plug in x equals 0, so that goes away, that goes away, that goes away. It's -12. But this form is good for finding the x-intercepts. So x-intercepts at 2. I suppose I should put a nice at symbol there. And since this is a multiplicity of 1, which is odd, I know it's going to cross. I have another x-intercept at -2, and same thing. It's an exponent of 1, which is odd, so it'll cross. And then I have an x-intercept at -3, and because this is a 1 exponent, which is odd, it'll cross. Cool. Let's see. What do I do next? Oh, end behavior. Let's think about the end behavior. Well, you look at the highest exponent, the term with the highest exponent, which if it's the standard form, it'll be the lead term. When x is really huge, that's what end behavior means, this will look like y equals x cubed. And what does that look like? It'll be climbing in this quadrant, and it'll be sinking in this quadrant. Look at all this beautiful information we have. Once you've got all this beautiful information, you say, hey, let me make a graph. So I've got x-intercepts at 2, -2, and -3. So I got to go out at least this far. X-intercept at 2, where I'm going to cross. An x-intercept at -2, where I'm going to cross. An x-intercept at -3, where I'm going to cross. A y-intercept at -12, and I'm just going to do this. Say that that's -12. Now my end behavior says I should start down here, and I should end up here. Now, let's see now. Let's do that. I'm coming up, cross, cross. Go through the y-intercept, of course. Cross. Hey, not bad, huh? Not bad. I don't know, wasn't that just fun? That was just great. We got it. So notice what I'm showing you here. I'm showing you a way to bang out a graph. A fast way. A way to hurry up and make a graph, right? Notice I didn't worry too much about, I didn't worry too much about how high exactly does this thing go. I didn't, I'm not worried about that kind of stuff. I just want to know, where does it cross my axes, and what's its basic behavior, what's its end behavior, what's it doing between, what's it wiggling like. That's all we really need. That's all I'm really interested in for this section, which makes it quite fun, I think. Let's do another one. Oh, 4 terms again. Looks like we should be factoring by grouping, except before I factor by grouping, first of all, I never do like leading with a negative. That makes me want to pull a -1 out right away. Except notice also there's a 2, a 4, an 8, and a 16. We could actually pull a -2 out. That should be the first thing you always do, is try to pull something out. So step 1, I'm going to be factoring, and I'm going to start by pulling out a -2. Maybe we'll make that a square bracket. So I've got an x cubed here. This will become a plus 2x squared. This will become a -4x. And this will become a -8. Right? Right. And I think I'm going to move that because I don't want to be going so far over there. Cool. So, continue factoring. Got my -2, I got my square bracket. Okay. 4 terms, factor by grouping. So from the first 2, I can pull out an x squared, leaving me an x plus 2. From the last 2, I can pull out a -4, leaving me an x plus 2. Okay, cool. So I've got a -2 square bracket. I do have a common term in both, or excuse me, a common factor in both of these terms. So I can basically pull it out, and I'm going to do it this way. Right? I pull, both of these terms have an x plus 2, leaving an x squared minus 4. Okay, close my square bracket. And then to be finished, this is g of x, I guess, I need to do that difference of squares. And I don't need the square brackets because that's just redundant, right? So x minus 2, x plus 2, and then hey, look at this. We got another x plus 2, so that's going to be squared, really. There's our factored form. Cool. What's the next thing we do? We find intercepts. We have a y-intercept at what? Well, this is the easy way to find the y-intercept. When x is 0, boom, 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 it's a 16. To find the x-intercepts, well, that's the easy way to find the x-intercepts. At 2, and since it's an odd exponent, the default exponent's 1, it's going to cross. And at -2 with an even exponent, so it's going to bounce. Cool. End behavior. What's my end behavior? Well, you look at the lead term, basically, which was there before I crashed it out. -2x cubed. Now remember what x cubed looks like? It looks like this. Doubling it just makes it a little steeper, but the negative is huge because that's going to flip it over. So it's going to be high in this quadrant, low in this quadrant. Okay, and now we've got so much information that the graphing is almost an afterthought. So let me get my intercepts down here. I got one at 2 where I cross. I got one at -2 where I actually bounce. Okay, cool. Y-intercept is at 16. I'll just kind of do this. Let's see. I'm supposed to start up here. So I'm going to start way up there. I'm going to bounce off of that thing. I'm going to go through this intercept. It says to cross, so I'm going to cross, and I'm going to hope that I'm supposed to go down, and yes, I'm supposed to go down. How's that? How's that for fun? That's like too much fun. That's huge. Hugely too much fun. We shouldn't be allowed to have this much fun. All right, another one. We're moving now, eh, folks? So the first thing to do is factor. That's always the first thing to do. It's a trinomial. That's where you try to unfoil, right? X to the 4th, break it up as x squared times x squared. 36, trying to find two numbers that multiply to 36 and add to a 13, actually -13. That'd be 4 times 9, right? 4 times 9 will work. So I want -4 and -9, really. So I have a -4x squared and a -9x squared would give me the -13x squared. Yep. And then I would have a -4 times a -9 gives me a positive 36. Yep. So good. And then our fully factored form is when we take care of these differences of squares. So that's going to give me an x minus 2 and an x plus 2. That's going to give me an x minus 3 and an x plus 3. Factoring is handy, ain't it? So there we go. We've got our fully factored form. Next, what are the intercepts? Well, we have a y-intercept at 36, plugging in x equals 0 there. And we have an x-intercept at, well, you look at this thing and you say I have an x-intercept at 2, multiplicity 1, which is odd, so cross. X-intercept at negative 2, multiplicity odd, so cross. X-intercept at 3, multiplicity odd, so cross. X-intercept at negative 3, multiplicity odd, so cross. End behavior is going to be, look at the lead term. That one, the one with the biggest exponent. It's just y equals x to the fourth. X to the fourth is one of those kind of parabola-ish things. So it's going to look, it's going to be climbing in the, over on the left here, and it's going to be climbing over on the right here. And with all of this information, we can now say, hey, let's draw a nice graph. Okay, x-intercept at 2, crossing. X-intercept at negative 2, crossing. X-intercept at 3, crossing. X-intercept at negative 3, crossing. Y-intercept at 36. See, if you label it, that's good enough. Who wants to get out a graph paper with 36 squares tall? I don't. So anyway, in behavior, we're expecting to start up here. So I'm going to start up here, cross, cross, go through the y-intercept, come down towards this one, cross, cross, and notice I'm ending like I want to end. Put your arrows. It's got to look something like that, right? Cool. Cool. Again, I don't know if, you know, maybe this goes like way down. I don't know. I don't care. I just want this basic behavior. Just find the basic behavior. That's all we're doing. Okay, so now I have to bring up a question. How do we know? These are polynomial graphs, and as you see, they can get wiggly. How do we know that we don't have more wiggles? Maybe down here it kind of does something like this. Maybe over here it kind of does something like this, right? How do we know whether there are more wiggles? And it turns out there's something we can use that doesn't exactly answer the question directly, but it gives us a humongous piece of information. Back to page 2. So I got to go back to page 2. It's that thing that I skipped. It's the degree rule. This thing tells you about how many times the graph can wiggle, or maybe instead of saying wiggle, I should say change direction. So like, I'm going up, I'm going down, I'm going up, I'm going down. So that counts as 1, 2, 3 changes of direction, okay? The degree of a polynomial, which again is the highest exponent, minus 1, tells you how many changes in direction are possible. How many changes in direction are possible? So look at this one. What's the degree? The degree of this one is a negative x times, and then if you FOILed this out, you get another x squared. So it's like a 3, right? I guess you would say right away that your end behavior is negative x cubed. But the degree is 3. So that tells me it can change direction. You have to subtract 1, 2. Change direction up to 2 times. That's what the degree rule is telling me. Now let me erase all that just to be neat. I'll write the same thing again. But let's pretend we were just graphing this thing. Let's pretend we're graphing this thing. It's already in fully factored form, right? So what's the y-intercept? You'd plug in x equals 0, and that's going to make it 0. Okay. What's the x-intercept? Well, you have an x-intercept at 0, right? This gives you an x-intercept of 0. Exponent is 1, which is odd, so it crosses. And you have another exponent here, because the function will equal 0 if you plug in a negative 2. This has got an even multiplicity, so it's going to bounce. So I got those 2 x-intercepts. Okay, and then the end behavior would be, well, we already figured this out. you imagine if this thing were multiplied out, you don't have to multiply it out really, you just have to know what's the first term going to be. This is a negative x, and when you FOIL this out, you know it's going to be an x squared plus some other stuff. So your end behavior is going to be a negative x cubed. Now remember, x cubed goes like this, but the negative is going to reflect that. So the end behavior is going to be not up, not down, but up. Not up, but down. It's going to be like this. So if I go to graph this thing, y-intercept at 0, x-intercept at 0, and negative 2. It's crossing here. It's bouncing here. It's supposed to come down. It's supposed to bounce. By the way, where's the y-intercept? Oh, it's at 0. So it goes like this, and then it's crossing there. Okay, so that's what the graph is coming out like. Now, check against this degree rule. How many times did this change direction? It changed direction 2 times. 2 changes of direction. 2 changes of direction. It was degree 3. You can look at this, by the way. Degree 3 says we could have 2 max, 2 changes of direction max. So there's no more wiggles are possible. No more wiggles. Can't be wiggling any further. No more changes of direction. No more wiggling. So we know that the graph has to look something like that. It's got to. Compare to this one over here. It's in fully factored form, thank goodness. We have a y-intercept at, well, if you plug in x equals 0, the whole thing's going to be 0. We have x-intercepts all over the place. We have an x-intercept at 0. What's the multiplicity there? It's an exponent of 1, which is odd, so it crosses. We have an x-intercept at negative 2. Bounce, because it's even. We have an x-intercept at 3. Cross, because it's odd. We have an x-intercept at 4. Bounce, because it's even. We have another x-intercept at negative 5. Cross, because it's odd. Whew. Okay, so, oh, and then by the way, the end behavior. The end behavior. Y equals. Imagine foiling that out. You'd have to have some time on your hands and some dedication to check your work. Wow. So anyway, but we don't have to, because we know that when we FOIL this thing out, we're going to have x to the 5th plus junk. And when we FOIL this out, we're going to have x to the 4th plus junk. Right? That's going to be an x to the cubed plus junk. That's going to give us an x to the squared plus junk. That's got a negative x. So doom, doom, doom. Just multiply all this stuff together. The lead term is going to be a negative x to the 1, 2, 3, 4, 5, 6, 10, x to the 15th. Negative x to the 15th. Well, all that matters is that it's an odd exponent. Remember the odd exponent graphs, x to an odd, looked like that, but wait, we're reflected because of that negative. So actually the end behavior is going to be more like this. It's going to be high here, it's going to be low here. That's our end behavior. Okay, can we start making a graph? Let's see now here. I sure have a lot of intercepts. I think I'm going to try to shrink this down first, just to give me some room. Not that. Room. I want room. Rim. I want a rim. Okay. Oh, why is it so touchy? Come on, you. Shrink. Why? Why? What's happening? What's the matter? You don't like my fingers? Good enough. Stay there. Okay. So, anyway, I wanted to start making a graph of this thing. Got x-intercepts all over the place. So we're going to cross at x equals 0. Cool. We're going to bounce at negative 2. Cool. We're going to cross at 3. Cool. We're going to bounce at 4. Cool. We're going to cross at negative 5. Look at all this. That's a lot of intercepts. Boom, 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 boom. Okay. The end behavior is supposed to be starting up here. Starting up here, crossing, bouncing, crossing, crossing. Kind of missed. Let's do that again. Crossing, bouncing. Notice the end behavior matches. So we say, wow, look at that. But then we have to say, hey, wait. In fact, this is probably a fuchsia thing. Fuchsia thing. Fuchsia thing. Yeah. So, wait. According to the degree rule, this thing could change direction up to, and remember the degree rule gives you a maximum. It doesn't tell you that it will cross a certain number of times. It gives you the maximum. But the degree was 15. So you subtract 1 and you say 14. It could change direction up to 14 times. How many times is this thing changing direction? Well, let's see. 1, 2, 3, 4, 5, 6. That's only 6. So as many as 8 more times. So that's the limitation to our method when we have really humongous polynomials. If we have lead terms that have very high exponents, we're not necessarily going to capture all the behavior. Notice how well it worked over here, though. The degree of this polynomial was only 3. We said, well, we could have up to 2 changes of direction. That's all we got. And so you're very confident. You say, yeah, the graph's got to look something like that. Whereas when you get these kind of polynomials where the degree is 15, then it's like, well, I mean, unless you happen to have 14 or something x-intercepts to play with, you're probably not going to know where all the wiggles are. Let's see. Did I look this one up? I don't even know. But how would you figure this out? How would you know? I have to continue down here. To find out whether there are more changes of direction, you have to either use calculus or Desmos.com. Let's spell that out so you can see it. Desmos.com. This is the best free online grapher I've ever seen in my life. Desmos.com. If you could actually just type in this function. Take a while, but you could type in this function and it would graph it for you, and then you could look at it and you'd have to zoom all over the place, probably scroll up, scroll down, scroll left, scroll right, zoom in, zoom out. You'd have to carefully look at this thing, and you could spot, does it do something weird? Maybe it does do something weird up in the air, or maybe it does do something weird down here. Okay, so that's the one weakness to our method, is we don't necessarily capture all the changes of direction when we just go through the x-intercepts. But let's go look at the examples we did here. What was the degree of this one? Degree 3. Degree 3 means 2 changes of direction are possible. And guess how many we had? We were going up. Down is one change. Up is another change. We had 2 changes. It's good. No more wiggles. And by the way, this is what this part of the instructions mean. Consider what the degree rule has to say. The degree rule says, yeah, that's all the wiggles you're going to get. Example 2, what was the degree of this one? Oh, another degree 3. 2 changes of direction are possible. And once more, that's what we've got here, because we're going down. Up is a change. Down is a second change. We changed twice. 2 changes are possible. Good. No more wiggles. No more extra wiggles. What about this one? This is the one where I was saying, oh man, maybe it's got extra wiggles, right? Well, the degree of this one is 4. And so you can have up to 3 changes of direction. And notice that that's what we've got here. Down. Change once. Change 2 times. Change 3 times. 3 changes. No extra wiggles. So I can go ahead and erase these because no because it's degree 4. It can only have up to 3 changes of direction. This already has 3 changes of direction. Our graph is accurate. Okay, so now I can use the full method on our last one. So this is our grand finale here. So, step 1, factor. Well, thank goodness they factored for us. By the way, notice, well, yeah, you can't really, if you wanted to factor this further, you might have to, you can't factor that further. Never mind. So let's look at the intercepts. Where's the y-intercept? Well, if you plug in x equals 0, that's going to make the whole right side 0. So the y-intercept is 0. That wasn't bad. Now what about the x-intercepts? Well, you could have x equals 0. That would make the whole thing 0. Right? What we're doing now is we're setting the function equal to 0. So you could have this term equal, this factor equals 0. It has multiplicity of 1, so that means it's a cross. Or if this was a negative 4, the whole thing would be 0. Multiplicity 1 again, so it's cross. Here we have an x-intercept at 3 with a multiplicity of 2, which is even, so it bounces. And then notice here, what's my x-intercept? What x-intercepts do I get from this? Well, to find out, you'd have to take the x squared plus 2 and say, well, when does it equal 0? Subtract 2 on both sides, take the square roots of both sides, and those are not real. There are no x-intercepts coming from that. This is not giving us any x-intercepts, okay, because it's imaginary intercepts don't count. They're not real, man. So that's it. That's all my x-intercepts. That's all my y-intercepts. What's my end behavior here? If you imagine foiling this thing out, what would we have? We'd have an x squared from this. We'd have an x squared from this. We'd have an x from this. And we'd have a negative x from this. So that's a negative x to the 6th. X to the 6th, you'll recall, is one of these kind of dealies, except we have the negative flipping it upside down. So our end behavior is going to be something like this. So let's start graphing this thing. X-intercept at 0, where we will cross. X-intercept at negative 4, where we will cross. X-intercept at 3, where we will bounce. We'll be coming from down here and crossing. We'll be coming over here and crossing. We'll be coming over, back up to bounce off. Then we'll go back down. Then we'll go back down. So that's pretty good. We got the same. We got the end behavior that we were expecting. Okay. Now comes the part about question. Are there any more wiggles? Well, it's a degree 6. That tells us up to 5 changes of direction. How many does this have? I changed direction 1 time, 2 times, 3 times. Only 3. Could change direction 2 more times. Could. Not saying it does. I'm saying it could. According to the degree rule, it could. Now, the changes of direction would have to be like, up here someplace, something like that. And how do you find out? Yeah, you go to desmos.com. And I did. And just to take the suspense away, I'll just tell you what I got. What I found was that no more changes of direction. So that's kind of nice. So this graph really does kind of capture the behavior. Although I should mention, this was down at like negative 80. It really sank quite a bit there. So that sank at negative 80, and if that impresses you, this was way up at about 1200. So that was a heck of a graph to look at. But like I say, we're not that interested in this particular lesson. We're not that interested in, well, how high did it go? Well, how low did it go? If you take calculus, it's actually, well, I wouldn't say easy, but you can figure those things out too. You can figure out exactly how high does it go, exactly how low does it go. We're not going to use calculus in this course, so we're not going to worry about it. And besides that, lots of times engineers, they don't care about precise details. They care about the overall behavior. Where does it cross and or bounce? What's the end behavior? These are the things that matter. These are the things that tell you whether the bridge is going to blow down in the wind like that galloping Gertie, or whether the wings are going to flap off the airplane or stuff like that. You don't need to know exact graphs, but you do need to know key features. Where's the intercepts? Where does it change direction? And what's the end behavior? So that's all we're doing in this lesson. So, and besides, that keeps it fun, right? Keeps it fun.